Okay, so last time we talked about flow control. All right, so these are some very important concepts in networking, and they're not necessarily that easy to understand. And so I just want to do a quick review because we're going to build off of everything we learned last time. We're going to build off of today, and so I want you to have this base knowledge before I start going into the details of TCP. Otherwise, you'll be completely lost. So let's just quickly go through these. Who can tell me what flow control is? Basically, with flow control, we want to match the sending rate to the receiving rate. Spelled that wrong, but so we want to match these two rates. Right? So that the sender doesn't necessarily overload the receiver. And we also, along the way, don't want to overload anything in the network. And overloading things in the network, preventing this, is called congestion control. Now, who can tell me what a segment is? Exactly. So it's just the transport layer name for a packet. So we'll say it's a part of a message. Now, does anyone know why we need to break our messages up into these segments? It's one thing that might not be that clear so far. So the message might be larger than our buffers. So we need to break it up into pieces that will fit in our buffer. And also, that's one reason. The other reason is that we don't have a guaranteed connection between the endpoints. So we can't just send the whole message at once because this bandwidth isn't reserved. And if we try that, we'll lose our entire message if there's, like a loss in the network or something. So instead of sending it all at once, we break it into little pieces so that if part of it's lost, we can retransmit that individual piece and keep going and just have a little bit of loss, all right? It's much easier to make up for losing, a small part of your message than losing your entire thing and trying to resend the whole thing, okay? So a buffer, so it's a bucket that holds packets until the system's ready for them. I'm going to say segments. Sorry. All right, so we need these buffers in order to just keep track of these messages, and then the sender or the receiver can deal with them as they're ready for them, right? So we talked about, different variants on flow control. And what's open loop flow control? So no feedback between the sender and the receiver. All right? So because there's no feedback while we're actually transmitting data, we have to negotiate the details of the connection ahead of time. And that's what admission control does. Admission control only lets in the connections that you know you have enough resources to support. All right? So we only allow access from these connections we know we can support. All right, and an example of that is when you have dial-up internet, where you have one T1 line and it can support 24 dial-up customers at once. And if it's full and you want to connect to the internet, you just have to wait until somebody logs off and then you can take their spot. All right? So this is an example of reserving the resources up front for the users. All right? Whereas in closed loop flow control, there is feedback between the sender and the receiver. And so because there's this feedback, we don't need to have a reservation system. All right? So this uses the notion of statistical multiplexing. And statistical multiplexing lets us take a channel that won't support all of our users concurrently. It only supports a small number of our users concurrently. But because they're generally not all sending or receiving at their full rate all the time, then we can take advantage of that fact and do this statistical multiplexing. And we can, moreover, we can change the sending rates of the senders so that if, for instance, there's 100 senders all sending at once, we can drop them all down to just get a small share of the bandwidth. All right? And we're going to talk about, this is what we're going to talk about today, is closed loop flow control in the form of TCP. All right? So TCP is one transport protocol. It's the most commonly used transport protocol on the internet today. And it does this closed loop flow control where it matches the sender's rate to the receiver's rate, and at the same time, it prevents congestion in the middle of the network. All right, so we'll get into that, but let's finish reviewing some of these concepts that we'll need. So an ACK, this is short for acknowledgement. So an ACK is just an acknowledgement that the packet was received. So I'll just put ACK that the packet was received. So acknowledgements are good for doing a few things. They're good for reliability, because if you don't get an acknowledgement for a segment, then you know it was lost somewhere in the network, right? So you can use acknowledgements for reliability, but today we're going to learn how to use acknowledgements for flow control and congestion control, all right? And that's really, that's the contribution of TCP. And that's actually what makes it really cool, is that using just this simple concept of acknowledgements, you can do all these things. You can do reliability, flow control, and congestion control. All right? What is a timeout? It's the time that if we haven't received an acknowledgement within this time period, we assume that the packet was lost. All right? So after this amount of time, all right, and then can someone tell me what a sequence number is? All right, so it's just a number assigned to the packet to help with this acknowledgement thing, all right? So a number assigned. Okay, so these are the basics of flow control. And now we're going to build on these to show you how TCP works. So like I mentioned, TCP provides reliability. It provides flow control and congestion control. Okay, now the cool thing about TCP is that it does all three of these things using the same mechanism. In fact, these are all very much coupled together, and you can't really tease them apart. It's really hard to provide flow control without also providing reliability. And if you can do congestion control, then you also get flow control and reliability for free. So today we're going to focus on TCP's congestion control, because if we can do congestion control, then we have the other things, all right? And you'll see exactly how this works today. So last time we left off at TCP's flow control in our just general discussion of different ways of providing flow control. And TCP's way of solving this flow control problem is that the only information you know is that a packet was not delivered. All right? So we want to provide all of these, and the only thing we know, so let's say the only information is did the packet make it? So by answering this question, we're able to do congestion control, flow control, and obviously reliability. All right, so the last time I introduced this concept of a window, of a transmission window. And we're going to denote this transmission window, the size of it, by W. All right, so we use W. And can someone remind us what a transmission window is? It's the number of unacknowledged packets we're allowed. So now an example of this is, if you recall, we talked about this stop and wait protocol, where the sender sends one packet, and then once it receives the acknowledgement, sends the next one. So that's an example where the window size is fixed to 1. You can only have one acknowledged packet out. All right? Then we also talked about, well, you can easily generalize that and have a static window protocol where you can have a certain number of unacknowledged packets out there. All right? But these aren't very efficient, especially for networks where there's a high round trip time, right? Because if you send a packet and then it takes a very, very long time to receive your reply, you have to wait and do nothing until you receive the acknowledgement, and then you can send another one. Now, if the round trip time in the network is very small, then you can send pretty quickly because you get the acknowledgements back fast. All right? So the performance of protocols that use a static window is dependent on the round trip time of the network. All right? That should help you with your homework if you're stuck on that question. And all right, so TCP, now we're going to introduce this dynamic window. All right, so how does TCP regulate its transmission window? Well, we talked about this last time, but I'm just going to go over it again just because you really need to know this stuff very well to understand TCP. All right, so your window starts out at size 0. So initially, we have the window size is 1. All right. Then we have two different phases. You start out in this slow start phase. And for slow start, each time we receive an acknowledgement, then we increase our window by 1. All right, so we increase it by 1 for each acknowledgement. So this means that every round trip time, if there's no losses, we double the window size. All right. Now to see this, let me draw. If you guys remember from last time, we have this diagram where we have our source and our destination here. Time is moving down. And we will denote sending packets by a line from the source to the destination. So in slow start, the source can sends one packet, all right? So our window size is 1. So this is the number of unacknowledged packets we can have out, and so we only have 1. Now, once we receive this acknowledgement, oh, wait, sorry, let me draw this in a different color to simplify things. Now, once we receive this acknowledgement here, then we just follow this rule, and we add 1 to our window size. So now our window size is equal to 2. So the sender can send 2 packets. All right. And at this point, we receive a reply. So our window size is equal to 3. And now that we've received this acknowledgement, we only have 1 unacknowledged packet out. So we can send 2 more. All right. And while we're doing that, this other acknowledgement comes in. So now at this point, we have our window size equal to 4. And so we increase our window size to 4, and we can send 2 more packets. And then these acknowledgments come in, and the same thing happens that for each of these, we send out more. And so I'm running out of room to draw these lines, but you can see that we'll have 8 lines. The lines are running into each other. 2, 3, 4, 5, 6, 7, 8. All right, so you don't need to keep doing this because this is doubling every round trip so that it gets carried away pretty quickly. But you can see that this was one. So this was the first round trip, all right? So this is RTT1. Then here was RTT2. Remember round trip time 2. Here's round trip time 3. So as promised, we're doubling this window size every round trip, all right? And the reason why that is because when we send out these two packets, we get 2 acknowledgments within that round trip time, so then we double it, right? So because we add 1 for each packet. All right, so this is called slow start. Not slow start, sorry. Just slow start. And this is to sort of find how much bandwidth is available in the network. All right, so we're sort of just probing and increasing our sending rate very rapidly so we can find, well, what's the maximum rate I can send? Now, once there's a packet loss, you'll switch out of slow start mode. All right, and I'll go over exactly what happens when there's a packet loss, but let me describe the next stage first. And the next stage is called congestion avoidance. And in congestion avoidance mode, we don't want to grow as aggressively because we're trying to avoid congestion. And so now, whenever we receive an ACK, so when ACK received, we set our control window equal to its current size plus 1 divided by the current window size, all right? So this means that we can have a fractional value for our window, all right? We can't actually send out fractional parts of packets. So we'll just round to the nearest integer when we're sending packets, but we want to maintain this fractional size. And the reason why is because how much does this increase the sending window each round trip time? Doesn't double, because here it doubles when we increase the window size by 1 for each ACK. But here we're setting it much smaller. We're increasing at a much smaller rate. We're only increased. This is the increased part. We're increasing by 1 divided by our window size. So this means we actually only add 1 to our window size each round trip time. Now let's look at how this works. So again, we have our same source and our destination. And let's suppose we're in this congestion avoidance stage. So we send, and let's say that our current window size is, let's say 2 to make it a little more interesting. So we send out 2 packets. Then we receive the acknowledgments for these packets. So this was 1 round trip time from here to here. All right, let me switch over to this side then. Our source, we have our destination. Our window size is 2. So we send out 2 packets. We get 2 acknowledgments back. And we get these acknowledgments within 1 round trip time. So this is round trip time 1. And once we receive this first acknowledgement, so let me draw over here, our window size is now equal to 2 plus 1 divided by 2, right? So it's 2.5. Then now when we receive this next acknowledgement, our window size is now equal to 2.5 plus half of that, which I guess is 3.25. So we've added 1 plus a little bit of slop onto that, all right? But if we take the nearest integer, then we've just added 1. All right, so this continues, and you can see that now, so now we send 3 packets out. For each of these, we increase our window the same amount, and so every round trip time, we've increased our window size by 1. All right? So now I've drawn it this way with these sort of just showing the communication between the source and the destination. But how does this actually look like if we were to look at the window size of the sender? All right, so to see that, we have this chart across the bottom, this time, and then the y-axis is the window size. All right, so if we're in slow start, this window size grows exponentially like this. All right. Now, once the window size hits a certain threshold, we'll just call threshold. Once we hit this threshold, we switch over to congestion avoidance mode. All right, now setting this threshold, we're not going to go into details about how to set that threshold, except we won't go into details about how to initially set this threshold, but we will dynamically change this threshold, all right? So we hit this threshold, then we switch over to congestion avoidance mode where we only increase the window size 1 each round trip time. So then we get this linear growth like that. Okay? So we went over this stuff last time, and where we stopped was what happens when there's a packet loss. All right, so does anyone have any ideas what we should do to this window when there's a packet loss? So let's just say for now, when there's a loss, all right, so let me draw a different chart here so you don't clutter up your notes overwriting things. So we have this window again, we have time. Now, on the other axis, I'm going to draw the buffer size, all right? So this is the buffer at the bottleneck. Now, if you don't know where the bottleneck is, it's just the point in the network where it's the sort of the choke point. And you can visualize it, if you think of pipes, you can visualize it as like the skinniest pipe connecting a bunch of pipes. So let me draw that. So if we have our source here sending some flow, which we'll just say, we can roughly model as water, and we have it going through a bunch of different pipes here, and they have various sizes. Well, the bottleneck, and then here's our destination. The bottleneck is this pipe right here, the skinniest point, all right? And we're doing like pretty simplified analysis here, so we're just going to assume that this bottleneck point is the only place where congestion occurs, right? Now, this may not be true in the network, and where the bottleneck is will actually change and so on as traffic patterns change, but for our discussion, we're just going to keep it grounded and just assume that there's a single bottleneck, all right? So now let's look at what happens if we just step our window back by 1 whenever we notice that there's a loss. And now you can just assume for now that we detect a loss based on a timeout. All right, so we do our slow start, we switch over to congestion avoidance, and let's say that here, there's a packet loss. All right, so packet loss. So we step our window down by 1, and we go back to congestion avoidance mode. Well, at this rate, we're going to get another packet loss. So there's a packet loss there. So we step back one. Again, at that rate, we have a packet loss. And so we get this really small sawtooth pattern. Right? Okay, so that's fine. But let's look at what's happening at this buffer. So I'm going to draw that in the orange chalk. So our buffer fills up here, and it sort of trails the sending, right? And then it starts to linear fill up. And then once we get here, the buffer is just always full. It's completely full, right? And so this is fine, except we're really having a lot of packets fail. Like every other packet we send is going to fail, right? Because our buffer is completely full, and then so we back off one, it gets time to drain a little bit, but we keep sending, so it maintains, it's full all the time. And now we have to consider we want to do congestion control, so we're going to have multiple senders sending at once. And a good analogy to think of congestion control is if you're on the highway and there's like they close down a lane, what happens? So if you're driving on the 401, it's construction, they close it down to 2 lanes. Even though they've just decreased the throughput of the road, a little bit by 1/3, then congestion happens very quickly and it gets backed up really far, right? So cars keep piling up because cars are coming in at the same rate, but they're not draining very quickly from this buffer, which you can think of as the highway. And so they back up, and it just keeps backing up and backing up until you really slow down the rate of cars that you're putting into the highway. All right? So we're going to take a break now, but after the break, we're going to discuss how to fix this so we don't keep these buffers full all the time. All right? What happens if we just step back by 1 whenever we detect a loss? And we sort of looked at this and we saw, well, okay, you're keeping the buffer full all the time. And now we're keeping the buffer full all the time when we just have one host sending. So what happens now if we had multiple hosts sending? So let's draw this same sort of picture. We have time across the bottom and our window here. And so now we have 2 senders. We have sender 1 in white, sender 2 in blue. So sender 1 starts first. And it starts doing this sawtooth thing. And sender 2 comes along here and tries to send some data. Well, right away, the buffer is going to be full, right? So it starts encountering packet losses right away. And it backs off by 1 each time there's a packet loss. So it also does this sawtooth pattern. And it's not ever going to be able to get any more of its share of bandwidth than just this little tiny bit. Because this guy's got the buffer all the way full. Whenever it detects a packet loss, it's just backing off a little bit. So the buffer's totally full all the time. And this guy can't get very much bandwidth. It can get a little tiny bit, but not much. So this is really, really unfair, right? So if you recall from last time, we discussed this notion of fairness. And fairness means that if you have n senders, then each of them should get 1/n of the transmission rate, the transmission bandwidth. Right? This isn't even close to fair. The first guy can totally hog all the bandwidth in the network, and even if we have multiple other people enter, they also only will get a little tiny fraction because this guy's sending window never decreases enough. All right? So what TCP does instead is it uses this rule called additive increase, multiplicative decrease. All right, so yeah, if they start at exactly the same time, then they'll sort of grow together, hit the congestion point at the same time, and then do that sawtooth thing, right? But when one starts before the other one, this guy, his window size is already this big, so he's already just blasting away at this rate. and not decreasing it really ever, right? Like, I mean, a little bit, but not much. And so this guy can't give very much of the bandwidth if he follows the same rule. All right, so we're going to assume for now that all the senders are following the same rules, all right? That there's no like malicious players and stuff. All right, so to solve this problem, TCP does additive increase, and then multiplicative decrease. And you can abbreviate that with the handy acronym AIMD. All right, so if that helps you remember it, then use that acronym. And so what TCP does is when it detects a loss, we cut the window size in half. And the intuition for this is if we go back to our highway analogy, where we have, this bottleneck in the highway and cars are just, the congestion's really building up and it backs up forever. If we want to decrease that congestion, the buildup of cars, we really have to decrease the amount of cars that we're sending in dramatically, right? We can't just say, oh, let's just cut back a little bit the number of cars entering the highway. We really need to cut it like in half in order to decrease the congestion so it can clear up and then you can start sending at a normal rate. All right, so what this looks like, if we draw the same type of picture, so we have our window versus time. Again, we do slow start, switch to the congestion avoidance phase. Okay, so here there's a packet loss. So now we cut the window in half. Let's cut it all the way down to there. All right. And then we stay in this congestion avoidance mode, so we keep growing like this. At this point, again, we'll have a packet loss. We keep doing that. All right, so we get that same sawtooth pattern, except now it's much more pronounced. All right. So let's look at what happens now when we have two senders. All right, so we have sender 1 sends, okay. And let's suppose that here, sender 2 comes along and starts sending packets. So I should draw that in slow start. So it's in slow start. Well, at this point, the buffer's full, so they both encounter a loss. All right, well, we'll just assume that they do it at they notice the loss at the same time, just to simplify things. So this first guy cuts his window in half, and the second person also cuts their window in half. All right, and then they resume in congestion avoidance. So we keep building at the same rate, and now we've gotten to the point again where the network's congested, and we have a packet loss. So they both cut their window size in half. Okay, and they keep sending. And they have another packet loss. So they cut it in half again. And so forth. So you can see that pretty quickly here they're converging to the exact same rate, right? Now they're totally synchronized in this case because I'm assuming that the losses are happening at the same time. All right, so that's why their sawtooths are going to, at this step, they pretty much overlap. All right, so it's something like this. And then from there on out, they'll get exactly the same amount of bandwidth. So it does take a little while for them to converge to the same bandwidth to get, to a fair solution, but it happens pretty quickly, and it does happen, unlike the case where we had an additive decrease. All right. And if we were to throw in more senders and if we had 4 or 5 senders, you see the same thing. That once we introduced, if we introduce another sender at this point, then these guys will eventually bring their rates down and we'll come to an equilibrium solution. So the question is on how do you detect loss? So basically, I've just assumed that you do a timeout means a loss, right? But you're saying that there'll be this duplicate ACK, and that also means that the packet was lost. And that's true. And so actually TCP handles, there's 2 different loss cases. Okay? And we're gonna go into those now. So let's recall the way that we can notice packet loss. All right, so the first is a timeout, meaning that this sender sends a packet and maybe it gets lost or its acknowledgement gets lost, and then after some period of time, we say, oh, okay. And I'm going to start using sequence numbers now, all right, to simplify things. So this is packet 1. So after this timeout, host A, we'll use host A for the sender. Host A says, okay, packet 1 was lost, right? But during this time, it might have sent more packets because its window size, let's say its window size is 3. And so it might, if these actually make it to the destination, it could receive acknowledgments for packets that, were actually did arrive, even though they were sent after the one that was lost. But so after this timeout, what happens is the sender will revert back to the sequence number where the packet loss occurred, and will start sending from there. All right, so go back to sequence number that was not ACKed, or sorry, to the packet with sequence number that was not ACKed. All right, and then you resend this packet and everything after it. All right, so we even though these were acknowledged, these did eventually, acknowledgements came in, we're just going to assume that they were lost, all right? So we resend packet 1, 2, and 3. And we need to adjust our window size. So, okay, the question is, what is a host or end host or anything? It's just a generic term for an internet device, all right? So if we're talking about an end host, it could be a mobile phone, it could be a tablet, a PC, a server, anything like that, all right? It's just, a host is just a device that is on the internet and communicates with other end hosts. Okay, so it's just a generic term for internet speaking device. Okay, the question's like, do you really need to resend all these, basically? And you can optimize this, however, the basic TCP, the original one, doesn't. So there have since been optimizations to it to do that, but what we're going to talk about, we don't need any of these optimizations. All right, so we know now what to do as far as resending the packets, but we don't know what to do with our window size. So we're going to, in this case, we set our window size back to 1, and we enter slow start mode. All All right, so let me draw the picture here. We have time again and our window size. All right, so we do slow start, we go to congestion avoidance mode, and here we have a timeout. So we set our window size all the way back to 1, and we do slow start again. All right. And also, we change our threshold. So if you recall, this threshold was the point at which we changed. So we cut our threshold in half as well. So threshold. All right, so now we have our new threshold is down here, half as big, so we enter congestion avoidance mode soon. All right. So now a timeout is considered like a pretty bad form of packet loss, and I'll explain why after I explain the other way we detect packet loss, which is called a triple duplicate ACK. Okay. So to understand this, let's again draw the same type of picture. And here, the sender sends packet 1. All right. And then packet 2, 3, 4. And this acknowledgement for packet 1 is lost. All right. However, the acknowledgements for packet 2, 3, and 4 make it to the sender. All right. So the sender at this point knows that something happened to packet 1. Right? It was probably lost. Maybe its acknowledgement was just really delayed and came in out of order. But we're going to assume that it was lost. So at this point, we say, okay, packet 1 was lost. Because we got these, so we got 3 acknowledgements for packets that, were out of order before we got this acknowledgement for packet 1. All right, so what we do in this case is we set our window, so we cut our window in half. W is cut in half, which is what I was previously showing you. And we set our threshold. We also cut our threshold down. Threshold is set to our new W after we cut it in half. All right. So what this looks like is we have time, we have our window, we do slow start. This is our first threshold. We switch to congestion avoidance. Okay, there's a packet loss. So we cut our window. So our window was here. We cut that in half to now down here. And we set our threshold to the same value, which in this case is pretty much the same. So this is the threshold. All right, and then we stay in congestion avoidance. Okay, we stay in congestion avoidance, so we grow linearly again. All right, so this is a good question. So why for a timeout do we cut the window all the way back to 1? And the reason why is that, all right, so suppose we have this triple duplicate ACK. Then we know some packets made it through to the destination, right? Because we're getting acknowledgements for packets. So we know that at least one packet was lost, but subsequent packets made it. So there's not that much congestion in the network. There is some, because we had a loss, but there's not necessarily a lot. Where here, where we had a timeout, So this timeout is assuming that there's not a triple duplicate ACK before it. So let me show that. So we have these 4 packets coming in. Let's say that this acknowledgement for packet 1 was lost. And this one's lost. This one comes away down here. And this one's lost also. So our timeout is here. So we only received 1 acknowledgement before this packet's ACK timed out. So that means that there is a lot of congestion in the network, right? Because we're not receiving acknowledgements for very many packets at all. And because of that, we really want to cut back our sending rate, right? We want to drop it really far down. And then we enter slow start mode so that we grow it, we grow quickly and we sort of probe for additional bandwidth. So you can think of slow start mode as this probing phase where you're attempting to find bandwidth in, what's the limit that you can send. You are cutting back your sending rate, but there's not a loss in efficiency because there's buffered data that will go through the network. It's just currently buffered, yeah. All right, so the question's about, is there a timeout every time there's a packet loss? And it's not necessarily true because you can have this triple duplicate ACK thing can happen before the timeout occurs. So let's say we send packet 1 here. And our timeout will draw like this. So our timeout period is down here. And we have our window set to size 4, let's say. And so this acknowledgement is lost. All right. But before our timeout occurs, we get these 3 acknowledgements for the other packets. So that means we can detect the loss before the timeout actually happens. I mean, okay, so yes, this is a contrived example where I set everything exactly right so it would happen. However, this does commonly occur in the internet, all right? Your window size is typically going to be more than 4, all right? So you'll be sending many, many packets and then you'll have a loss, all right? So even if your window size is like 1,000, you still count the triple duplicate ACK. The 3 acknowledgements for packets before, all right, so let me draw the sequence numbers on here. This is packet 1, 2, 3, and 4. So if we assume that the acknowledgements are labeled with the sequence numbers, so this is 1, this is 2, 3, and 4. So the triple duplicate is these three acknowledgements that we received out of order. All right. So we should have received acknowledgement 1 first. However, we received 2, 3, and 4. So this is like a triple ACKs for, out of order. Okay, so the question is basically how often do packet losses occur? So packet losses occur all the time. Actually, TCP is designed to cause packet loss, right? So you can think of it as it's sort of inefficient in a way because TCP, the way it figures out its sending rate is to force the network to be overloaded, to force a packet loss, right? So packet losses happen all the time. I mean, you can run through some of these scenarios on your own and sort of look at how it operates, yeah. Okay, so yeah, this stuff is kind of hard to get your head around, I admit. And so one question that Ishwinder was asking me about is this: how does the window size relate to your actual transmission rate, to how fast you're actually sending packets? Because this window size is the number of unacknowledged packets you have out in the network. So it's the number of packets you're waiting to receive this ACK back for, right? But it's not exactly how fast you're sending the packets. But they are related, right? So the higher your window size, so as we see in these examples, the higher your window size, this means you're sending more packets per second, right? And so if you're sending more packets per second, you're sending at a faster rate. So if your window size is 1, then you send 1 packet per round trip, right? Because you need, and what I mean by round trip is that we send, and then we have to wait to send another packet until we receive this acknowledgement. So this is the round trip time. It's the time to get from the source to the destination, and then back, to hear back from the destination, all right? So this is 1 round trip time. All right, so our sending rate depends on our window size and the round trip time. All right, so the smaller the round trip time, the faster we can send with small window sizes. And to see that, let me draw a different picture here. So if we have a very, very small round trip time, our lines will sort of be almost horizontal like this. All right? So we receive this reply really fast. Now, let's just assume that we're doing something like a static window for now, and we get these back quickly. So these 2 hosts, in this amount of time, they sent 2 packets. There was 2 packets sent from the source to destination. Now, if the round trip time is longer, let's say it's double as long, then in that same amount of time, we can only send half as many packets. All right? Because we have this very long round trip. So the congestion window is related to the transmission rate, but it's not exactly the same as the transmission rate. All right? So I'm going to just go through the final details of TCP, and then we'll do a little bit of analysis if we have time on this stuff. So just the other details of TCP that we need to worry about is, well, there's a couple things. All right, so if you remember from last time, you open a connection with this 3-way handshake in order to, just to initialize the connection. Well, to close the connection, you do something similar. So to close it, whatever end host wants to close it says, I want to close it. So say the end host who wants to close it, they send a fin message. All right? And the other end host acknowledges the fin. So it acts that, and it sends its own fin message. Okay? Then finally, the original end host, let me just call this guy end host A. So then A acknowledges the other fin. Okay, just so you know how to close a connection, all right? So there's this, actually a 4-way message passing. So there's a fin, an acknowledgement of that fin, and then a fin from the other guy, and an acknowledgement of that, all right? Now, the other way that a connection can close is a different timeout here, is a timeout. So if you haven't heard from the other host within a certain amount of time, usually something like 30 seconds, then you just say, okay, this connection's dead, and you drop it, all right? Now, the other thing that we need to know how to set is how do we set these timeout values? So how to set the timeout for packet loss. And to do this, we measure the round trip time. All right, so we measure the RTT. So recall we have something like this. Grab a different color chalk. So we know what this RTT is here, right? And we can keep track of that. And so as we're communicating with the other host, we measure what the RTT is, And then we set our timeout to always be slightly longer than this. So we have the timeout is greater than or equal to the round trip time, then plus something to account for variance. So I'm just going to say some. I'm just going to say something because you don't need to know exactly what this exact formula is. Just know that we add a little bit on there. All right, and this, if you really want to know, this uses a moving average. All right, but you don't need to know that. Just know that the timeout has to be greater than the round trip time. Okay, so in the remaining few minutes, let's look at how well does TCP perform. And one of the questions we'd like to know is, what's the average throughput of a TCP sender? Now, if you're not familiar with the term throughput, it's just equal to the transmission rate. I don't really know why we have so many terms for the same stuff, but this is the way it is. So throughput is equal to your instantaneous transmission rate, all right? And we want to find this average throughput rate. Well, the throughput is on average, it's equal to our window size divided by the round trip time. All right, now to get a little bit of intuition behind this, if we did something like where we assume we have a static window where we do like the stop and wait protocol where our window size is always 1, so let's say our window size is equal to 1, then every round trip we're sending 1 packet, right? And so that means that we're sending exactly this. We're sending 1 packet every round trip time. And if we were to have a window size of 2, you could see that we're sending 2 packets every round trip time and so on. All right? So if we assume that on average a loss occurs, so I'm going to use capital W to indicate the window size when a loss occurs. And I'm going to make one more assumption, and that is that the loss is always detected by a triple duplicate ACK, right? So loss all right, so this assumption just means that we will never go into the slow start phase. All right, we're just always going to assume that we're in congestion avoidance. All right, so with these assumptions, and we're going to assume one more thing, which is that the round trip time and this capital W are constant. For the duration of this connection. All right, then if we analyze this and look at what happens to TCP sending rate, we see that it will vary between this lowercase w and the uppercase w. Or sorry, let me just draw the picture and I'll explain it. So we have time again across the bottom. This is our instantaneous window size. And then we'll say that our big W is up here. So capital W there. Then what happens is we're going to ignore slow start. So we send to here, and then we have a packet loss. So whenever there's a packet loss, we cut our window size in half. All right, so this point right here is equal to the capital W divided by 2. So we cut our window size in half. We're still in congestion avoidance, so we increase linearly. Up here, packet loss, cut it in half. All right, so we just do this sawtooth pattern between W, capital W, and W divided by 2. So what's our average throughput now? 0.75 W, and if you remember, I said the throughput depends on the round trip time as well, so we have to divide this by the round trip time. So this is throughput is equal to this. Okay? Because that's just this line down the center here. Okay, so are there any questions about this? All right, so for next time, we will talk about other ways to do transmission control. So an example is, suppose that you have a protocol where you want to communicate with outer space, and TCP is very bad in that case because the round trip time will be very large. So we'll look at protocols like this.